It's a pleasure to have you, and welcome.
Hi, everyone. Thanks for inviting. And I'm also excited to be the first speaker. So yeah, feel free to ask a lot of questions. And yeah, I guess I'm a little more from the machine learning background and not so much the vision. So like a lot of interaction is like totally welcome. And hopefully we'll have something interesting to take away. Um, okay, let me start. Yeah, I guess it's 2021 and we don't want bad news, but unfortunately, I'm going to start my talk with some, not so great state of affairs of current machine learning systems. So, here's the task of that is particularly relevant in these days. So we want to do online content moderation. And so it's kind of nice if we can do this automated. And so like, Google released this Perspective API where they try to detect toxicity of comments using machine learning. And, the sort of the usual machine learning pipeline, we get some training data. And so what they did for this API was to like, source a lot of online comments from these forums and that have humans to annotate these comments. And so the system, seemed to work pretty well on some examples, like, if these sentences look very similar to the training distribution. For example, here's a comment, like, if you think differently. And so this, what do you say, the API detects this correctly and, it says it's toxic and it stops it from being shown. But now we are in a world where people want to evade these systems, right? So turns out that it's actually very simple to do so. So if you just carefully insert a typo, like shown here, then the same API is going to say that this has very low toxicity and lets your system lets it go through. So if this was a human annotator, they probably would still call this toxic. But like when we try to automate these systems, like it's kind of easy to break these systems when they use machine learning. Right, and so something like that people here are probably more familiar with is adversarial examples in vision. So here's an example like of a lake shore that I just downloaded from the internet, and then I ran it on an ImageNet classifier, and I get like it's a lake shore with high confidence. But now I can add these really small perturbations where each pixel has changed by like some 0.005 over here, and you get an image on the right that looks identical on the screen to me, but the same classifier now calls it a laptop. Because maybe they were ahead of their time and predicted the pandemic where we should have been on vacation, but we are stuck in front of our laptop. But really, this is a very easy, very easy to generate adversarial examples and break current vision systems. And this was like shown in 2013, I guess. And so after that, there have been a lot of different ways to break systems. For example, there was this study that showed you can have like 3 stickers that are carefully placed on the road and then cause your Tesla to go onto oncoming traffic. And you can add these stickers to stop signs and cause them to be misclassified as like yield signs. And this is another interesting study that showed you can have these colorful glasses and then cause a facial recognition system to recognize you as someone else completely. So to keep things short, it's like systems work really well when your test distribution is very similar to your training distribution. But the moment you allow people to actually interact or like do something with the system, they can find these very easy ways to break current systems. So another example is slightly different from that of the adversarial example context is like how spurious correlations can break systems. So this is a real life study that was done. Not real life study, but like this is an example from Amazon where they tried to make their lives easy and use an ML tool to select qualified applicants based on their resumes. And of course, so the training data was basically successful applicants from the previous years. And you can imagine that, if you look at training data that is, constructed this way, they're going to pick up biases. For example, like 80% of the people were like male because of like, we all know about the gender bias issue in tech companies. And at test time, again, if you have a resume from the same distribution where most of the resumes are male, the system seems to work pretty well and you get good accuracy on average. But when you take a closer look and look specifically at how the system performs on female resumes, for example, even if that's not part of the resume directly, like the fact that someone is a netball captain could actually lead them to have lower scores. So the model kind of associate because of the bias in the training data picked up the spurious correlation that like if you are say a netball captain, then you're probably a woman, and that meant that you're not a successful applicant. This is another issue with current systems where when we just have like a lot of training data, there are these spurious correlations that the model can pick up, and we don't want that to pick up when we actually deploy these systems in the wild. Another example is with like, when you're trying to use machine learning for healthcare. So this is like the task of detecting whether someone has a collapsed lung or not. And you can have a lot of x-rays and train a model. And it seems like this model does well. For example, on this image here, you pass a machine learning, you pass it to a model, you get a prediction that this is a collapsed lung. which is correct. But then when, on a closer inspection, it turns out that what the model is actually using is this spurious correlation here. So you can see this highlighted region as like something called a chest drain, which is basically a treatment for collapsed lung. So in your training data, since that it was obtained from hospitals, most of the people for whom the collapsed lung was detected also had a treatment for them, which was the chest drain. And so when we fed this to a model, the model was essentially learning that chest drain was predictive of the collapsed lung and not really looking at the lung structure. So in particular, the model had really poor accuracy on patients who had collapsed lung but did not have treatment because the chest drain was absent in these cases. And this is pretty problematic because this is exactly the demographic that you want to actually detect because you want to treat these patients. So yeah, so I guess these like examples kind of highlight that we need to think about machine learning beyond just the training distribution. And so one convenient way to think about this is like, you want to be close to the training distribution because it's too much to expect that the system just does well everywhere. But at least you want to have good performance across a family of distributions around your training distribution and not just exactly on the training distribution. Right, so one way to think about this is like, in the standard setting that we typically study in our machine learning class, and a lot of benchmarks and a lot of the progress that you've seen is when your training distribution and your test distribution are the same. So you have held out examples, but they are from the same distribution. And in this talk, I'll be focusing on the robust version of this question where at training time, you have some distribution, but at test time, you care about not just that same distribution, but a family of distributions around it. And so for people who are familiar with the robust optimization, this is under the classical robust optimization setting. And so what is this family of distributions that we'll think about? So you could consider many different settings. And in this particular talk, I'll focus on two cases. One is like subpopulation shifts, where you have different demographics in your population, and the training distribution has one particular ratios among these demographics, and you want to do well across all of them. Like for example, in the male versus female setting of the recruiting systems. And the second part of the talk, I focus on adversarial examples where instead of getting good performance only on a test point from the distribution, you want to do well across a set of perturbations around that test point. Okay, so with that, I'll jump right in. If there's any questions, feel free to unmute and ask whenever. Okay, so the first part of the talk is based on work that with Shiori, Pangwei, and Percy at Stanford that we had at ICML this year. So I'll kind of have a formal setup and then describe some empirical observations and provide like a simple model or a simple story that kind of tries to explain some empirical observations, and we'll look at how we can fix some of these issues. So just to recap, like we had this problem that models can latch on to spurious correlations. And these are basically misleading heuristics that may be there for a lot of the training examples, but they're not really the true things that we should learn, and they don't always work. For example, the collapsed lung and the chest drain. So to keep things simple and not have any medical jargon, let's look at just classifying the birds. And so let's say this is an input bird that we're looking at. And the machine model, and the task was to decide whether this bird is a land bird or a water bird. So this is a simple classification task, binary classification. Now we introduce a spurious correlation in terms of the background. So you can imagine that if we just download a picture of birds from the internet, a lot of water birds are going to have water background. And so the model could use the background to decide whether something is a water bird or not. And in fact, that's what happens. So if we have a water bird and a land background, for example, that is shown here, since the model basically uses a spurious correlation, the model would get it wrong because the background does not match the actual label. So this is a task where we're interested in deciding whether something's a land bird or a water bird, and the spurious correlation that we'll be thinking about is the background. And our goal is to learn machine learning models that can identify the right label without losing the spurious correlation. So how do we model this? So how do we cast our goal? So the way we look at this is, to keep things simple, we consider 4 different groups, right? So we have these groups are determined by, the spurious feature or the non-robust feature, the background, as well as the label. So there are a lot of points, for example, in this majority group here, where the background and the label matches, which is like why the spurious correlation could be picked up. Similarly, there are a lot of points where the land bird is in land or the water bird is in water. But we also have some examples where these spurious correlations do not hold up. So we have some examples where there is a water bird in a land background and vice versa. So these are the points in the off diagonal over here. And we can say that a model is robust to spurious correlations if it gets good performance on all four groups, right? Because it also gets good performance on water birds in the land background. That means the model is not using the background to predict the label. But if it weren't the case, then if the models use spurious correlations, then they will get good performance only on the majority where the background and the label matches, and they will do pretty badly on the minorities. So this gives us one way to evaluate whether models are robust to spurious correlations or not. So when we just do standard ERM, we get good test error, like as with a lot of deep learning systems these days. And on average, the error looks pretty good. But the worst group, which is example over here on the off diagonal, the minorities get already like up to 40% error. So what happens is because of this, because of this spurious correlation, the model is actually using the background to predict the label, because of which it gets really poor accuracy when we evaluate on water birds in land background or land birds in water background. Right? And so our goal is to use this setting of these groups or these subpopulations and try to address this issue where the model is using the spurious correlation. So what kind of robust training could we do? Right, so the obvious strategy that we could try is to upweight the groups, right? So with the reason we had this disparity could also be that majority of the groups had the spurious correlation working, but minority was where the spurious correlation was flipped and the model was doing wrong. So now we could try to get good performance on all these subpopulations by upweighting the minorities. So that's basically this reweighted estimator that I wrote here, where we look at, for a training example, we check which group it's in, whether the background matches or not. And what we do is we artificially upweight the points in the data set where there are water birds in land background or land birds in water background, hoping that that teaches the model to look at these points more carefully and therefore not use the background to make the prediction. And in fact, whenever there is a class imbalance or this kind of subpopulation imbalance is a very common estimator that people use in practice, where you try to account for the fact that you have a fewer points from some group by increasing the weight on those groups. Right, so this is basically ERM that we had earlier, where when the label matches the spurious correlation, things work well, but off diagonal they work badly, and you have high worst group error. And now, so now the goal is to whether reweighting can fix this issue. So ideally, we want reweighting to get good performance on all four groups, so that you have good performance on average as well as the worst group. And such an estimator would rely on the robust feature, or would not use the background, and hence obtain low error even when the background doesn't match. So this is our goal. So let's try to train this model using this reweighted estimator, and let's look at performance. So we look at two different data sets over here. One is water birds, which is like what I described so far, where the task is to determine the type of the bird. Then the other example we consider is celeb A. So we consider like a kind of a toy task where we know there is a spurious correlation. For example, let's say we want to predict hair color. And it turns out that in the celeb A data set, like most of the blonde celebrities are female. And so the spurious correlation is is the gender. Right? So when you're trying to predict hair color, it turns out that if you are male, you are more likely to have black hair. And similarly, if you're female, you're more likely to have blonde hair, because males with blonde hair are less than 1% of the training points. So the spurious correlation in this case is like gender, and the spurious correlation in water birds is the background. So now we try to artificially, upweight these points where the spurious correlation is not present, or it's in the opposite direction as majority of the points, and look at what this estimator does on the worst group error. So these are the trends that are plotted here. So we vary, the width of the ResNet, and so we try to increase the size of the models. And in the water birds, we look at random features, and we increase the number of features. So one interesting thing that we observed is that as we increase the size of the model, the worst group error started increasing. So this is like kind of opposite of what we know when we do like normal training, where we use bigger models and things work better. But when we did this reweighting and looked at this worst group error, what we found is that like as we increase the size of the models, for example, in Celebabe, it keeps increasing the error. And in Waterbirds, we get some kind of a double descent, but the error on like these bigger models, like the second descent is not lower than the first descent, right? So what this says is that the best model when we want to be robust to like this spurious correlations was like actually smaller models and not bigger models. So this was something that was quite counterintuitive, especially because we were always used to like just making the model bigger whenever we wanted to see an improvement in performance when we do normal machine learning. Right, so in other words, we found that we really need explicit complexity control when we want to avoid this issue of using spurious correlations. And this could come from either like, a weight decay that we're familiar with, early stopping, or like decreasing the number of parameters, which is kind of what I showed on the plot here, where we changed the size of the model and found that smaller models work better in being robust to spurious correlations. Right, and just to make sure we're on the same page, like when we do average accuracy and standard training, the kind of double descent that we're used to, and there's a lot of theory as well as like a lot of experiments to show, is that we expect a curve like this, where as we increase the size of the models, things work better. In particular, we don't see any like when we control the complexity of the models by restricting the model size, it doesn't offer benefits for the average accuracy. So this was something that we found pretty interesting when we looked at robustness, and kind of told us that we need to rethink some of these some of the common intuition that we have from machine learning about whether bigger models always help. And we found that in our case that wasn't really the case when we wanted to be robust. Right. So just to simpler list to like a schematic for kind of what we're trying to study is when we look at this worst group error, we find that overparameterized or like big models where you get zero training error, they have higher worst group error than smaller models, like which would be the regularized version. But when we look at average error, for both estimators, whether you reweight or you just do ERM, we find that bigger models are always better. So there is this tension in like how model size affects performance in terms of the robust accuracy or the worst group error and the average error. And so like in the next few minutes, I'll try to shed some light on like why this is happening, like why does overparameterization or having bigger models make things worse for robust accuracy. I guess if there are any questions at any point, please feel free to unmute and ask. Okay, so here's, sorry?
I have a naive question about the previous graph. Are those two figures in the same scale? Like the whole double descent phenomenon also like was basically like we increase the parameter size up to a certain point, and then we keep increasing the parameter size to like 10 times or exponentially more, and then we observe this phenomenon. So I'm just like curious if you guys just normalize for that. Like if you keep
Right. Yeah. It's a good question. Like the scale is the same for both models. So we did look at the same. I mean, the range of models that we considered, like this is actually the same. And in fact, like we probably tried like an even bigger model, or like the biggest model that people kind of use these days, and we did see that the same trend. So yeah, it was not going down after a point.
Got it. Thanks.
Yeah.
I have a question also. So maybe you are going to answer later, but is the worst model, why is the performance of the worst set bad? Is because there is a larger set that is different, or is because it's a small? So like if you were to train that small subset of data alone without increasing the size, will it do better?
Yeah, so actually I will get to that in a bit.
Okay,
yeah,
great,
yeah.
Great.
Okay, so here's sort of like one way in which we can think about what's happening here. So each input has some robust features, like the actual size, like some property of the bird, and then there is this spurious feature, which is the background. And learning to use these spurious features is easy, right? So for example, like you could imagine that just classifying backgrounds is much easier than actually identifying characteristics of the bird and using that to decide whether it's a land bird or a water bird. But the problem is that this only works for majority of the points, doesn't work for the minorities. Here's like a schematic for thinking about this. So let's say you had like this non-robust or spurious feature on the y-axis and robust feature here. So majority of your points are actually separated by the non-robust feature along the x-axis, And I don't know if it's visible on the slides, but like, there are these minority points which are marked in crosses, which are on the opposite sides. And so they don't get classified by using, the spurious feature. But then like you can model the fact that the spurious feature is easy to learn by having this, sort of large separation between these two majority at least. On the contrary, learning to use the robust feature is harder, right? For example, learning the semantics of the bird is harder, but it works for all of the points. So the way we could think about this is like, let's say we have, because I'm just plotting linear classifiers, let's make this a little bit noisy, right? So let's make the robust feature a bit noisy and so make it harder to learn. And so in this case, we see that this boundary actually works for both, the crosses and the circles, but it's actually a bit hard to learn because, there is some noise or the separation is very small. And when you have a really complex model, the problem that happens is that you can memorize the minority points, right? So because you have such a large model, you can basically learn any arbitrary function. So for example, what it ends up learning is something that I plotted here, where you learn the non-robust feature that works a majority of the points, but then now you get some points misclassified, right? Like these crosses here, but you can essentially memorize those points, right? Because there are only few points and the model can just like learn to map that particular point to a label without learning a generalizing pattern. And now we can say we're upweighting the model, so upweighting these points, so shouldn't that help? But when we have a really big model where you can get zero training error, upweighting does not change anything because, at least like keeping optimization aside, in terms of just the loss function, the training loss is going to go to zero for all the points. And so just saying that this point should have low loss and increasing the weight on that point does not change anything because it already has zero loss. So upweighting, or whatever we try to do with that estimator in robust training, does not do anything when we have high complexity because the model can basically memorize these minority points and does not have to do any generalization. But on the flip side, when we are disallowing memorization, or when we have this low complexity, the model does not have the free capacity to do something like just learning some pattern for all these minority points without learning something that is simple enough to generalize. So now when we upweight the model, where the model has to actually it cannot memorize and it has to get low loss on these minorities because we've upweighted the points, that actually forces the model to learn the robust feature. So it actually forces the model to learn the minorities right by learning the correct feature. So the complexity control is very important here because if we didn't have that complexity control, then these big models would basically memorize the points, and there's nothing that we can do to tell the model to not memorize by simply upweighting the loss. So we have to be in this classical ML setting where we don't have excess capacity that allows us to just memorize the points. And when we are in that classical setting, we can control whether we learn the spurious or the non-spurious feature by upweighting these minority points. So we have some, theory about this. We can analyze this in a linear setting, and I won't go into the theory result, but the main insight is basically the same that we had earlier. And so, sort of to Antonio's question, so what are the two key factors that lead to this imbalance? So the two key factors that we get from the theory is that these majority points have to be much larger than minority. It's not just that the minority is small, but that there are these majority points which are much larger than the minority, and that it's easier to learn the non-robust feature than the robust feature. So for example, if the background was also hard to learn, then the model won't show this property of learning the background, right? So the background has to be easier to learn. And when that is the case, the model really picks up the background, especially when majority of the points are having that spurious correlation. So just to test these things, so we can't change, okay, so we can control via sampling the ratio between the majority and minority, right? But we can't change the actual hardness of learning these features because that's inherent to distribution. So now we kind of try to look at can we change the sampling of the majority and minority and see what the estimators do. So this is kind of like what Antonio was suggesting, one fix that we could have is to artificially rebalance these points instead of upweighting, because upweighting doesn't change anything, doesn't change the actual points or the cost associated with learning those points. What we could instead do is to throw away a majority of the points and this way balance the majority and the minority. So you still have very few training points, but now your majority and minority are balanced, and we can see whether this is what the system learns now. Right, so now we find something interesting that, like, when we do this balancing, we get back the curves that, we are familiar with, where the error goes down as the model size increases. And we get basically comparable performance of as to, whether we throw away majority of the points or we upweight and regularize. So I'll get to that in the next slide. But sort of the main takeaway here is that when we remove this imbalance between the majority and minority, we're back in our original, setting where bigger models do help. So we see, like, these curves go down as we change the number of parameters. Right, so subsampling is kind of the key factor, or like this group imbalance is the key factor that made overparameterization bad. And so if we remove that by subsampling, if we actually change the actual points we show, then it kind of helps overparameterized models achieve low worst group error. But this is obviously not a great solution, because we're now, if there's a group balance of 90 and 10, what this is saying is that you have to throw away 90% of your majority points, or 90% of your training points essentially, and then you can use big models. But if you want to use all your training points, then you have to use small models. Right, so kind of paraphrasing that, so we look at two different things that we could do. One is reweighting, where you keep the same number of points, but you just change that you just had a high weight on these minority groups. Or you could have subsampling, where you literally reduce the number of points from the majority. So when we do the reweighting, we get this curve that we saw earlier, where we have to use smaller models. But when we do subsampling, where we threw away a lot of the data points, we could use larger models. And these two we found that empirically, both of these were kind of the same. So the best performance you could get on the left side was kind of equal to the best performance on the right side. So in one case, we have to end up sacrificing expressivity, and sort of, most successes in machine learning because we have these really expressive models, but it's kind of sad that we have to sacrifice that if we want to, get good accuracy on minorities. And on the flip side, you have to either sacrifice a lot of data if you want to use big models. So in terms of the setting of using, these kind of upweighting based, estimators, if you kind of restrict yourself to ERM and you just change the weight of the points, so we do have this tension in these estimators that we could use. So either we use all the data or we use big models. We can't do both. So I guess I'll just try to summarize. So we started with this empirical observation that when we used reweighting, overparameterized models have higher worst group error, and so for some reason bigger models were using these non-robust features more. And so we tried to understand that and had like a simple sort of story where we had this notion that when we have big models, then they can do something very degenerate or memorize the minority points. And so it never really picks up the patterns from the minority when there is something very simple that it can do for the majority. And we got a fix of reducing this issue by kind of either we just throw away some of the points or we use a smaller model. And we saw that empirically both of these things kind of work as well, where you have either you reduce the majority minority imbalance by removing majority points, or we have to upweight the minority and regularize your model heavily. And so those were the two methods that we had that worked in practice. So this is so I guess I can pause and take questions before I switch gears to another kind of robustness question. Yeah, the one thing I do want to mention is so this kind of says that we really should be able to do better, right? So if all we can do by using upweighting is equivalent to removing most of your training points, then clearly these estimators are not efficient. And so there's a lot of scope to think about what are better ways to solve this problem. And there have been some new methods that people are now looking at, but most of them, they all kind of have the similar patterns. So we should think about some radically new methods of being robust, and simply upweighting these training points is not the best method, but that's kind of what we know so far.
In the second part of your talk, are you going to talk about something else, or are you talking about solutions for this problem?
And I'm going to talk about a different adversarial example, adversarial perturbations. So yeah, I'm going to talk about something else.
Okay. Are you aware of any work which is I love your experimental setup. I think it's really great. And the observation that reducing parameterization or subsampling both have good effects, but obviously there's a trade-off, which obviously leads to this question, can you do both? Mm-hmm. Can you reduce parameterization on only the subsample that you care about? Are you aware of any work in that direction or anything like that?
So if you reduce the number of parameters, if you subsample the points, then you end up in this curve over here where reducing parameters doesn't help. Increasing parameters helps. So bigger models do help, when you subsample the points.
So I understand that. I mean,
Yeah.
so if your picture is right, then the cool idea is that the overfitting that happens in the big model is that it's too powerful. It has too easy a time at memorizing the 100
Right.
training examples that are in the minority, or whatever the small number is, right? So you could imagine that when you actually do the training updates, when you teach it about what it can learn when it sees those 100 models, somehow you alter the update so that the model has fewer degrees of freedom. So just to reduce the parameterization, so it can't memorize those things. Maybe it's allowed to memorize lots of other things, but when it comes to these cases,
got it.
Do something. Are you aware of any work sort of in that direction?
So there have been some works that try to get at this intuition, but they don't work. Like they do something in practice, but not solve the problem entirely. So there's this Lipschitz regularization, I think they call it, but like people from Tengyuma's group at Stanford. So like, okay, there are two ideas you could do, right? So one thing you could try to do is you get to avoid memorization is to ask these minority points to have much larger margin than the majority points, right? So for each point, you could have a differential amount of margin that you enforce. So you could try to do that, and that offers some benefits, but you still have to upweight and do all these tricks. Only then it works. It doesn't solve the problem, but that gets at the intuition. So maybe you can refine that idea. The second thing that people try to do is this Lipschitz regularization, which kind of tries to enforce smoothness around a particular point, like so not just globally, but sort of data dependent way. So around some particular training points, you can enforce that the network is very smooth, and that kind of tries to reduce memorization of that particular point. But the caveat is that with these really big neural networks, like Lipschitz constant doesn't make sense, because like at a particular point you could have smoothness, but then you move a little bit and then things could change a lot. So it's really hard to enforce that. But that also kind of gets at the idea that maybe we could do some kind of data dependent, like regularization, either in terms of the margin or in terms of the smoothness, to ensure some points are memorized and some points are not. Like some points are not memorized at least, but they don't, like, these ideas are kind of preliminary and they don't work as well as just like what we have right now, because kind of the best interface to deep learning these days is to just like keep the data points as such and just change the weights or something, right? The moment you go into the internals, things get a little complicated.
Thanks, Aditi. Thanks for your answer. That's really helpful.
Thanks.
I also have a question. Here you assume that you have exactly 4 groups, 2 majority and 2 minority, and you also assume that you know them in advance, so you can subsample or reweight. Usually in the training data, you don't know these minority groups. Probably there is more kind of minority groups, how we can handle it or find those groups.
Yeah, that's a great question. I think that's like the important sort of like next question to think about, and we have some ideas here. So one thing that we could do is sort of use the cross validation loss in some way, right? So if you had some notion of like if you found irregular patterns in your data set where some points have higher loss when they are not trained on. So for example, these you can identify spurious correlations by the fact that if they're not in the training set, these minority points, you get low accuracy. So if you actually had held out data and then you had like different, like, if you found that there was some, grouping of points within the feature space where this set of points regularly had high cross validation loss, that could tell you that this is actually a minority group. So this is one thing that you could try to do to identify, what are the subpopulations latent in your data set. But so one kind of interesting thing over here is that how do you handle noise, right? So how do you decide whether something is noise or something is a minority? So you could also say that the reason neural networks don't do well on these minorities is because it looks like noise to the model, it just ignores them, right? So that's kind of another positive aspect of deep learning, is that they're robust to noise. But so that becomes a little tricky. And so I feel like the way to overcome that would actually to have some judicious supervision. So you need to like have some, experts to like disambiguate whether this is just a noisy point or this is actually a very different but correctly labeled point. And so if we could figure out a way to like decide which points to query the label on in an efficient way, then that can avoid this disambiguity. And I think those are sort of like how we can try to handle the issue of like figuring out what are the groups.
Thank you.
Okay, so let me, so I guess there'll be time at the end as well, if you want to have questions. So now I'm going to talk a little bit more about another surprising aspect, at least to me, when we looked at robustness. This is kind of in the vein of adversarial examples or perturbations. And so we actually perturb some training points. So this is work with Michael, Fanny, John, and Percy at Stanford. Okay, so quickly recap this, adversarial example setup. So you can think of the informal goal as to get high accuracy, not just on a test point, but also perturbations of the test point, right? For example, you could have these really imperceptible perturbations, and you want to be robust to them. So it's convenient to think of, this adversarial example sort of a game between, say, attacks and defenses. And so the goal of the attacker is to find some perturbation within this ball for which the classifier changes the label. And as a defender, the goal is to train a neural network that is, robust to all these perturbations or attacks. Right. And so you can think of one, the easiest example or set of perturbations to think about is sort of the one that I presented earlier, where we can write it as the following. So each pixel, you can think of an image, and you're allowed to change each pixel by a really small amount. And you typically keep this epsilon small so that the image that you get when you add these perturbations is essentially imperceptible. But as I said, neural networks break when you try to do this. And you can say, can we try to get neural networks that are robust to these perturbations? So that's kind of the goal. And so one thing before jumping into details, we can discuss more about this after the talk as well. So thinking about why this problem is, interesting, or sort of why I find this problem interesting. So one striking aspect is that these perturbations are so small that, they are imperceptible. So the image on the right, as you see here, is imperceptibly similar to the image on the left. And so this kind of says that the way current systems work, they work very differently from how we expect them to, right? So when we look at a given image and it seems like the model is giving the right caption or detecting the right object, we assume that it's actually reading the image the way we do. But the fact that these sort of meaningless perturbations can break your model, and the fact that they're so easy to find, says that there is very different methodology by which these systems work, and we don't really understand how do we bridge our understanding versus what these ML systems do. And so this looks also like a very simple, or at least when I started working on this in the beginning of my PhD, it felt like a very simple problem, such a well-defined problem. We should be able to solve this by doing some kind of robust training. But it turns out that so I guess from 2013 was sort of when it gained a lot of attention, and there's a lot of research interest in this problem. And after about 7 years, we still don't have a really good solution or understanding of this setting. And so it turned out that even the simplest definition of perturbations that you could think about, it led to a very challenging open problem. And this really lays bare some fundamental questions, without even thinking about what are the right perturbations or what is realistic and so on. So keeping those complexities aside, even with a very simple definition, this is already an extremely hard problem. And it kind of says that we really need to think about how we do robustness in ML. Anyways, with that, let me kind of jump right in. So let's look at the CIFAR 10 benchmark that probably a lot of people here are familiar with. And let's look at L infinity perturbations of some size. So don't worry about the size that much. They're kind of small so that they look pretty much the same. And so this is a table that shows two metrics that we care about, right? So one is accuracy on just a test set. And then we look at robust accuracy, where we're allowing attacks on the test set. So if we do standard training, we all know now, we get more than 98% accuracy. But the robustness is 0. Every test input can basically be perturbed. And these are kind of two important papers that had these robust training methods. And so so this is this kind of state of the art, essentially, where you get 44% and 53% robust accuracy. And the other thing that we observe is that the standard accuracy falls when we try to do robust training, right? In fact, any improvement in robust accuracy seems to come at a cost to the standard accuracy. So one thing that I was interested in is really the understanding why the standard accuracy falls. And yeah, so basically trying to understand, so this is not great, right? Because if we really want to build robust systems, and each time we make improvements in robustness, if the model is just getting worse at the task itself, then why would I even want to use this model? So when I thought about robustness, I thought of this as it should improve standard accuracy if at all, because it's making the model better. You're telling it to do more than just the task, and you're giving more information. And so I was very shocked when the standard accuracy seemed very consistently to be decreasing with robust training. And so this was one observation that we tried to understand. So what causes this trade-off? So abstractly, we can think of robust training as doing the following. So if we were doing ERM, we'd find you would minimize this loss of f, x, and y in your training set. But now when we're doing robust training, instead of minimizing just the loss on x, we minimize the maximum loss that you can obtain over a ball of perturbations. So one issue about the trade-off could come from the fact that instead of doing just x, we're looking at a ball of perturbations, right? So if this ball itself contains inaccurate data, so when we are training, suppose we are giving wrong information to the model, that's one way in which the accuracy will obviously fall, right? For example, if we're actually perturbing images large enough such that we're changing the label, but when we're telling the model to not change the label on these predictions, when we do robust training, that kind of says that that was going to affect your accuracy. But in reality, we're actually looking at these imperceptible perturbations where we are sure that within this ball of perturbations, the label doesn't change. So we are adding accurate data, but that is still causing a decrease in performance. Now, the other possibility, so let's shift our focus to looking at these, what is a model class we're optimizing over. So another obvious source of a trade-off could be if this model class is not expressive enough. So let's say we're trying to be robust, and this is kind of what our data set look like. If we're allowed to only use linear classifiers, then you can. So this is, I don't know if it's clear to see here, but any linear classifier would be, sorry, any robust classifier cannot separate your data set, and then you get this trade-off. So if you're restricting your hypothesis class in a way that you don't allow complex functions, then that could lead to a trade-off, because if you ask for robustness, like for example here, it's not going to be accurate. But in practice, we look at these highly expressive neural networks where we can actually learn some complex boundaries. And there is a nonlinear, robust, and accurate predictor, for example, here. And this is kind of the world we are in, where the training loss is 0 on both, or the standard points as well as the robust points. So we're able to fit everything on the training set. There's enough capacity, but still that causes a trade-off. So just to paraphrase, keeping out the obvious explanations for a trade-off. So even when we add extra training data in terms of these perturbations, so just similar to data augmentation, we're just adding perturbations, and we're adding accurate perturbations, which are actually label preserving, and we're having enough capacity. So then why still does adversarial training or this kind of perturbations affect accuracy? Right. And so informally, I would think of robust training as teaching the model something that I know about the task, right? So I know that when I'm looking at object classification, I am invariant to small perturbations. And when I try to give this information to the model actually generalizes worse than if it didn't have this information at all. So what we show is that this is not just an aspect that we don't know how to train neural networks well, or that there is something about the way we're doing this min-max optimization, but it's actually fairly fundamental, and this could occur even in a convex problem where we're optimizing correctly and in a well-specified, very simple problem. So we found that this notion of adding constraints or adding prior information that we know about the data set, and we give it to a model and we try to get good, we train the model, that could sometimes hurt accuracy. So this kind of data augmentation or this kind of incorporating prior information does not always help. Here's a very some intuition as to why this could happen. So when this is again a consequence of overparameterization. So we're no longer in the classical ML land where we have small number of parameters. So this overparameterization, the number of data points is much smaller than the dimension that we're operating in, or the number of parameters. So we want to make this linear. So something that's well studied is this abstraction where you could think of fitting the training points. So you get these linear constraints where you match the training data exactly, and you find the minimum norm solution that fits the training data. So we see that the inductive bias, so sort of what is the regularization in the model in this overparameterization, is to minimize this L2 norm of the parameter. Right, so this is a generic norm. But what actually dictates the test error is the data geometry, right? So the geometry of the data set is important in determining the test error, but the inductive bias or the regularization of the model is something that is agnostic to the data and is just the norm of the model. So this mismatch can actually lead to the issue that when we add constraints or we add training data, it can interact with this inductive bias in a way that causes it to have higher error. So I know this is a little vague, and I don't want to go into the math, but here is a pictorial illustration. So let's say our underlying function is the following on the left side. So we want to say do regression and fit splines on this function, and we have the staircase-like structure. So on the right, let's look at what estimators we could have. So let's say we only had these purple points here. So they come from the original data, and now we just did normal training. We didn't worry about perturbations. We get the blue line that is pretty accurate on most of the points. Now, let's say we taught the model to have the staircase-like structure. So I knew that about the function, and I tried to tell the model that. So I said that at every point, you also perturb it a little bit to the right and have the same label. So when we do this and then we fit splines again, so you get this orange curve over here, which kind of shows how by giving extra information to the model about the ground truth function, we have interacted with the generalization in a way that makes it worse than if it had just ignored this function, ignored this information at all, and just learned a linear function. So this kind of illustrates that there is an issue where the inductive bias of the splines, for example, just wants to be locally linear. So the moment it sees it down, it just continues down. And so that interacts with sort of the data geometry where there is this linear structure when we try to enforce some perturbations. So you could think of what is happening is that we are trying to give some information about the local structure, but the way the model uses this local structure comes at the expense of the overall global structure that it would have learned if it didn't worry about the local structure at all. Oh my God, sorry, the random animation. Okay, so mitigating the trade-off. So kind of this simplistic picture is kind of nice because it tells us that, so if there is really this tension between the local and global trade-off, then what we should do is first first learn the global structure and then append the local structure, right? So first do standard training, learn this blue line. And then now if you tell me to be robust to perturbations, then I can try to be robust to those perturbations. And so this kind of reminds us of this idea of robust self-training where, we do, okay, so I'll get to the algorithm, but basically the intuition is that we really use the fact that the standard estimator is good at capturing global structure, and then we try to use the standard estimator downstream and we try to also get robustness. So this is kind of the robust self-training algorithm, and I think this is kind of cool because we are used to thinking about self-training, but I'll hopefully illustrate why this is particularly interesting for robustness. So the first step that we do in self-training is just forget about robustness. Okay, so first in robust self-training, we assume access to some unlabeled data points. So assume we have a lot of unlabeled data. In the first step, we just forget robustness and do standard training, and then we get a classifier that I show here, for example. So we only look at the labeled data. And when we're doing the next stage, what we do is we take this classifier and generate labels on the unlabeled data. So we get the labels like here 1B. Now we do robust training on this entire big data set, so which has both the labels as well as the pseudo-labeled data, and then we get something like this. So why does this work, or why should we expect it to work? So one key thing is that we are in current setting where we are getting really accurate classifiers, right? So in step 1A, we have enough labels, for example, on CFAR, where we're getting above 98% accuracy. So 1A gives us a really good estimator. And since the unlabeled data is from the same distribution as the original, you don't have to be robust for the pseudo labels. You only need to be accurate because they are not adversarially perturbed. So they are data from the underlying distribution. So this pseudo labeling step really gives very good pseudo labels. And now we're in robust land, we are having much more data to work with. And importantly, on the unlabeled points, which capture some of the global structure, we are using the pseudo labels that come from the standard estimator. So you can think of the standard estimator gets those labels right, and we can really use that global structure and now enforce robustness, which also gives the local structure. So we show this in theory, and sort of the key insight is that when we train on these pseudo labels to be robust, it's kind of, you can view this as a data dependent regularization, which actually captures the structure of the geometry and regularizes your estimator towards the standard estimator, and hence captures the global structure. And at the same time, because we're enforcing robustness of these perturbations while we train, we also get the local structure. So this kind of gets at best of both worlds of being robust as well as accurate. So very quickly, we kind of extracted some unlabeled data from tiny images, like from this group, and we did this robust training. And so we see that we improve both metrics. So we improve the robust accuracy and we improve the standard accuracy as well. So of course, this doesn't like, go all the way, but like at least it's like, proof of concept says we see a big improvement in robust accuracy. And this is kind of the first method that actually improves the standard accuracy over other methods, right? So we don't see this trade-off in like previous methods as much. So we do mitigate some of this effect where we are compromising on global structure by fitting this local structure.
Hold on for a second. So for your robust self-training, are you doing the minimax training? Are you applying L infinity perturbations and everything? So what is the so I'm just trying to understand what is the need for the additional so I guess maybe I misunderstood when I first when you presented. I thought, oh, maybe the additional data points are the perturbed points, but is that not correct? You actually need different data points?
Yeah, so the additional points are actually unlabeled data from the original distribution. So for example, in this case, let me see if I can, so in this case, the additional points are like other points on the line. So basically what we're saying is that we need to capture the entire geometry. So we could just collect more labels and solve this problem, but that is expensive. So instead, even unlabeled data is sufficient because if we just didn't care about robustness at all, things are accurate. So we can use that estimator to get very good pseudo labels on a large unlabeled data. So now effectively we are spanning a much larger space. So we are getting the global structure because we're getting labels on all these points. And now when we introduce perturbations and train, we are able to retain our information about the global structure, but also capturing local information. So we're getting both accuracy as well as robustness.
I see. So there's this other paper, and maybe forgive me if it's actually your paper, which is about enforcing. It's actually about sort of out of unlabeled samples, out of distribution samples, where you add an objective to make sure that you've got sort of high entropy, or low classification scores that are also robust to changes, which seems really similar to your thing. How would you compare your approach to that one? Are you familiar with that paper?
Yeah, I think I know what you're talking about.
I forget the author.
Yeah, so the difference is that so they actually need that it's out of distribution, and so because of that, what you want to do there is to like not output confident labels. But in our case, we're really looking at these unlabeled points coming from in the distribution, so it's actually helping you for the task. And so the what value these unlabeled data is giving you is that it's capturing this global structure because you're getting labels from an accurate classifier. So you can effectively think of this as you're just giving much more data to your robust method, because of which now when we try to learn these perturbations, it no longer has a trade-off because it does not forget what it knows about the global structure from the standard estimator while still being robust. So it really uses the fact that the unlabeled data is from in distribution and tells you something about the task. Whereas in the other case, like you could consider a complementary setting just to like, make classifiers better would be that you just throw a lot of irrelevant data and tell your model to do badly on them. So that's kind of a slightly orthogonal way of doing,
Right, but robustly badly. Anyway, it's great. Thanks.
Okay, yeah. Okay.
I actually think that there is another relevant paper, which is by Zico Coulter, and the paper is Overfitting and Adversarial Robust Learning. He's also basically doing the same thing, and he says it's pretty much the only thing that helps overfitting in adversarial robustness. He calls it semi-supervised learning, and I think they're using the same data set. And
exactly. So they use the data set that so that's exactly. That's also very relevant. It kind of says that it's actually more relevant to the first part of the talk where, where regularization is important. So they say that they find that, for adversarial training, you do actually need to regularize as well. So you need to do early stopping much more so than for just like normal training. Okay, so
but
sorry, sorry, go on.
No, I mean, this is pretty much this approach just like sort of increases your data set size, right? I mean, even though you're using like classifier and some of your labels might be incorrectly classified, but it's kind of nice. So I guess it is essentially just increasing your data set size, right?
Exactly. Exactly. So one way to think about this is just increasing the data set size, because of which it can learn more complex functions well.
Right.
Yeah. Okay. Yeah, so I guess the summary is that, we need to be careful when we think about adding valid data. Like, my view was that, like, yeah, I'm telling it more information about perturbation, so it should generalize better, but that's not always the case because you have this interaction with inductive bias. And the nice thing is that, like, we really have an estimator that works well, which is a standard estimator. It's not robust, but we can use that and to fix our robustness issues. And so this robust self-training in general is very powerful, especially for robustness, because we are in this regime where we know how to get accurate classifiers. So we should think of ways to use these accurate classifiers, via unlabeled data. So we can easily increase data set size, and that helps robustness. And I just wanted to like say one quick slide because I know I'm out of time. And so far we've only talked about corrective measures, right? So we looked at like, we know things are not robust or they're picking up non-robust features. And we saw how we could change the training method to like explicitly tell the model not to do that. So either we upweight some points or we perturb the points and so on. And similarly, you could see that there are papers that show networks, prefer texture over shape, or like, like non-robust over robust and so on. So can we take a look back, a step back and think about why do we have this problem at all, right? So there are all these different predictive features. So can we understand which features does the network use versus the other? Like, why is this even a problem? And so one thing that we found in like a very simple exploration is that neural networks, like, so this is an example. So let's say this was our data set. And so we could think of two different kinds of boundaries. So one is this red boundary over here, which has this zigzag format, and one is this linear boundary green. So the red boundary is good because it has larger margin. So it is actually the max margin classifier with respect to the input. But we see that it's more complex, right? Because it has these, different piecewise functions. And the green the green boundary is less complex, but it has a much smaller margin. So we can expand this to d dimensions and see a much larger gap between these two classifiers. So can we say, what does the network do? So it turns out that the network only uses the green feature, right? So if we had different, input features and we had different kinds of boundaries, it turns out that the networks completely ignored any complex feature, even though it had a much larger margin of separation, and only used the smaller, margin of separation if it was more simple to use. Right, and so basically, like a lot of when theory papers look at deep networks, they look at these linear settings where in linear settings networks do learn the max margin classifier, which is sort of the best you could do. But when we have these linear or like more complex settings where different features could have different complexity, it turns out that the networks really have an extreme bias towards learning the simplest feature, even if the margin of separation or like within the inputs is very small. That kind of explains why they use like texture over shape. Like say texture is like it would have a much smaller separation than shape, but it's much easier to learn. So one way, like if you want to think about how to make ML more robust by design, is to see whether we can avoid this simplicity kind of bias and get networks to use all the features in your training data, and not just and it shouldn't just ignore some features just because they're more complex to learn. So thinking about how we can do this from ground principles, and sort of it could be interesting, but we found this very interesting bias that networks completely ignored anything that was more complex when there was a simpler feature to use. Anyway, so I just want to kind of now conclude that current ML systems are not robust, and I spoke about two kinds of corrective measures that we could do, where we do adversarial training when we perturb inputs, or we upweight the minority groups. But when we use these measures, we find some surprising factors, like how we need to rethink what data augmentation or what kind of adding data does, and we need to rethink whether big models are always better. And so the sort of interesting question is, can we make networks robust by design? And of course, there are questions of how do we bridge the gap between having these well-defined, mathematically defined shifts, or where we knew the groups, and how do we go to the real world? For example, can we learn more realistic perturbation sets? Like, can generative models capture better perturbations that we see in the world? For example, like contrast changes or brightness or something in a better sense than like these L-infinity perturbations. And can we automatically identify latent groups or spurious correlations? Yeah, with that, I'll wrap up and thank my funding as well as my wonderful collaborators. And yeah, thanks for inviting, and I'm happy to stick around and answer questions.
Yeah, that's great. Thank you.
Thanks, Aditi, for the great talk.
Yeah, thanks.
I guess we have time for one or two questions.
Hi, Aditi, can you hear me?
Yeah.
Yeah, Aditi, thank you for this wonderful talk. So I have one small doubt. So, I mean, see, one reason I can associate that why model is failing for this, for these adversarial examples, because humans are not perceptible to the high frequency information that is getting, contained in this noise. So
Yeah.
what if, simply we can put a high pass filter before applying those images to the model, then we don't need this technique. So have you, come across any work in that direction? And
yeah. So, okay. So I think back in like a few years ago, like a lot of papers are like with ideas something like this, but I guess so they do work to some extent, but the problem is when we are in this adversarial sort of worst case setting, like you can always break this by finding some way to break this system. So it's not going to be a perfect system. So if you're going to really think about the worst case robustness, that doesn't give you anything because you can break them. But if you just look at robustness on average to perturbations or something, like things like this do improve robustness.
okay, thank you so much.